Gautam has already said what my talk is about, essentially. So, but anyway, what we will see is that the main point of the punchline will be that NAdS2 behaves very differently from higher dimensional analogues of holography, and in a really rebellious and weird way. And hopefully, at the end of the talk, it will not suffer this fate that you will not to throw it out of the cannon. So this is actually an etching from Sepoy Mutiny. And so it shows actually these mutiny soldiers were actually tied to the cannon and actually blown with the cannon. I am afraid you might also like to do this to me after the talk. So we don't have cannons. So okay, so hopefully not. So let's see. So this is based on a paper that we are finishing now with Alexander and Lata. So Alex is my PhD student in Vienna. So this is Alex. I haven't put a picture of Lata because I thought Lata you all have seen her. But I realized that ICTS TIFR is also there, so so maybe I should have also put a picture of her. Okay, so actually, although however the title sounds and abstract reads, actually this talk is going to be really simple and stupid. It's going to be for the most part a technical talk, and so sorry for that. So essentially, the one good reason of studying NAdS2 holography is that it is supposedly very simple, and indeed it may lead us to understand some fundamental aspects of quantum gravity. So one of the interesting questions here is, of course, to understand the information loss paradox and to study in real time the evaporation loss. I mean, to have a controlled setting in which you can calculate an evaporation, Hawking evaporation process and other things. So the question, of course, is a toy example of quantum gravity, how much you actually learn about the real information loss paradox is a separate issue. But actually many kind of things do appear here, like the idea of gravitational memory and other things do appear here in many contexts, as you will see. So it's an interesting place to answer maybe some questions, if not all questions. And also, it's a gravity analog of quantum systems with maximal chaos. This is very well known, and this is why SYK became popular after Kitaev pointed it out. And perhaps we can learn some new things in this connection, because I think one of the interesting and major question is to understand how to translate many-body dynamics, not in the language of particles, but in the language of information. So instead of using a particle-like description or a kinetic theory-like description, maybe we can understand many-body process using information-like quantities. And this connection is indeed not so easy to make, but maybe large and limit holography can help us to make some connections in this regard of how to use quantum information to write many-body dynamics. And in both contexts, I think what is important is to study time dependence, because in the context of like Hawking evaporation process, you would like to solve this holographic theory in real time, and not only in Euclidean time, but in understand it in real time what is happening. And also, for example, you might like to understand say some very simple question like I want to study an OT-OC out of equilibrium and try to understand how the Lyapunov exponent is bounded even out of equilibrium or things like that. What are the general principles that bound the Lyapunov exponent, or how you can even define it out of equilibrium. So there are many such questions, and for all these questions, I think it's important to understand time dependence. And this talk will be about explicit construction of exact time, only classical time dependent solutions of this problem. And of course, to have some interesting time dependence, you have to perturb it, and I will perturb it by relevant deformations, because NAdS2 is an infrared CFT, and you can only perturb it by irrelevant deformations if it arises in some infrared limit. And along the course, we will see a few surprises, even before considering, correlation functions and quantum corrections, even just at the level of the classical background itself. And the classical background itself is not very something, at least according to me, it was not very easy to solve. It was not very easy for us to solve it. And there will be many surprises in such solution itself. But these surprises can actually help us to extend application of the simple holography rather than throwing it away. Actually, it will it actually it reveals some very interesting features of it, and it will help us to also construct useful toy models for some unusual, strongly correlated phenomena. And I would allude to some class of these examples, like behavior of quarkonia in quark-gluon plasma and something and some similar stuff. Okay, so I now start with the bulk point of view. So I just repeat the setup. And so essentially what we will do is study holographic interpretation of Teitelbaum-Jacques gravity. And indeed, it's probably the simplest 2D gravity with finite energy excitations. Is there anything simple than that? Just pure gravity with finite energy excitations? So, yeah.
No matter.
No matter, without matter. No, we have matter, we will add matter, but without even adding matter, this probably is probably the simplest example. Well, the reason is that if you do not have this dilaton field, this is simply a topological action, and therefore it will give you simply a bland answer. It will not have any dynamics. To create any dynamics, and the simplest way to create dynamics is to add this dilaton term, and this dilaton itself doesn't have any kinetic energy. It simply couples like that, and it basically enforces that that space-time is always locally AdS2 and nothing more, nothing else, because in two-dimensional space-time the only degree of freedom is the Ricci scalar itself, and if the Ricci scalar is frozen to -2, you will have locally only AdS2. So that's what the dilaton does, but it also creates finite energy excitations because this action is no longer on-shell a topological action. And it carries a cost of, so any diffeomorphism will carry a cost up to an SL2R transformation. That's what you will see. So this is the simplest action that you can think of, and you can add matter. But crucially, I probably should have written here explicitly. So the matter here, important part of the S matter here is that it only contains the metric and additional fields chi. It doesn't contain dilaton itself, so the dilaton doesn't couple to matter. And because the dilaton doesn't couple to matter, you can enforce the phi equation of motion simply enforces R plus 2 is equal to 0. That is, your locally your metric is just AdS2.
And that's the choice you
That's the choice, yeah. Actually, yeah.
Are the Einstein equation, the metric equation tells you what about phi?
Yeah, this is what we will come see. And then the other thing, of course, is that, yeah, so that actually comes from Shiraz's question that if you actually see the equation of motion for phi, you can impose this condition that, in fact, you also need to put it in to make sense of a variational principle. You just simply freeze the value of the dilaton field at the boundary, R times the value of the dilaton field. So the dilaton always grows as 1 over R asymptotically. That is, as R goes to 0. And it's important, in general, of course, this can be a function of time. And here U denotes the boundary time. So U is actually the time of the experimentalist, or the boundary time. So this is the experimentalist time. And you can specify that this is like a coupling constant. So you can specify, it's a dimension-full coupling constant.
Sorry, this is elegant question, I should know the answer, but just in the bulk, what is the equation for phi?
Yeah, I'll come to that. So this is this equation actually. I just, yeah. So so this actually is a function of time which you can choose to be whatever you like, but in this talk we will freeze it to a constant, and this actually will be the source of all our strange results maybe, because.
in the presence of an irrelevant coupling, there the asymptotic behavior of phi can be changed, right?
Exactly, because if you think of it as a lower dimensional or near horizon version of some kind of a higher dimensional black hole, then indeed this coupling cannot be independent of, say, I put a scalar coupling J of U, then phi B of U cannot be simply frozen, because one way to think about phi B U is some dimension of an extra circle of AdS2 times S2, so it's a radius of S2. And indeed, if you perturb some scalar field perturbation, and if you really state the back reaction and the actual full gravitational equations, that cannot be simply frozen constant. But just from the point of
view. For a lot of cases it can be, because you can derive, anyway we should talk later,
Oh, that will be wonderful to know. Actually, this is, you have,
Papers on this.
yeah, of course, you have that.
In
And
many cases you can, that's why I was curious to say that.
yeah, actually, yeah, so this is something we should talk, and I'll be happy if the answer is yes, that you can indeed make it a constant. So just to give some history here, that Almeri and Polchinski pointed out that one can use it to understand back reaction to near horizon geometry of near extremal black holes. So that is something, so it simply gives you a nice toy model of back reaction. And the holographic dictionary was also developed by Polchinski and Almeri and Polchinski. And further understanding, and actually much deeper understanding, has come from these works of Jensen, Engelsey, Mertens, and Verlinde, and there was also this paper in Malderson and Stanford Young. So there have been the 3 follow-up papers which actually nicely explain this very well. So, so what we say is that matter couples minimally to gravity and not to the dilaton. This is exactly what I wrote here. I should have written it explicitly in the equation itself, but I didn't do that. But so the dilaton equation of motion is r plus 2 is equal to 0, and it's exactly what I was saying. Space-time is always locally ADS2. It's simply frozen to be locally ADS2 by dilaton equation of motion. And let us define the matter energy momentum tensor as simply the variation of the matter action with respect to g mu. So only this part gives you t mu matter, and this is what I call t mu. Then the equation of motion of the dilaton will be simply this, and this satisfies the Bianchi identity if r plus 2 is equal to 0 is also satisfied. This satisfies the Bianchi identity. And
the matter in the bulk.
yeah, the matter is in the bulk. So actually what you should do, you should first solve the matter equations in just pure ADS2, because the metric is always ADS2. There is no back reaction on the metric. And then you substitute t mu matter here. And after you do that, you can find the equation of motion for dilaton. And so it apparently looks like it should be a very simple thing to do, but we found it's not that simple. And we assume here generic matter sector as of now, and diffeomorphism invariance of matter sector will also imply nabla t is equal to 0. Of course, that's required for this equation to make sense, because this satisfies the Bianchi identity, therefore so should the right-hand side.
So why isn't the solution just that you couple the matter appropriately to the Schwarzschild action? The boundary value of the matter is some time-dependent object living on that boundary. If you couple it to the Schwarzschild.
You can, but we simply don't do it.
No, but you can prove that that's equal to what we talking about.
Ah, okay, you can also get it from the, okay, yeah, so you can also, yeah, I will come to the, yeah, so what I will basically avoid doing is writing the boundary, holographic normalized boundary action. But indeed, if you do that, you also get the same equation. The reason we simply avoid doing it because we use this an explicit causal construction, so you have retarded propagator, which is not easy to obtain from a boundary action. So, but you can also do it that way, indeed. Yeah, it will be equivalent to do it.
If you have the so the situation here is that the important part of this text that is going to thing is going to be the this Goldstone set, the reparameterization in the elements.
Yeah.
Some f of the g and stuff. So for when that object is not there, then you know whether these functions of the matter
Yeah.
fields are.
Yeah. So here also you will see that, yeah, here also what you will see, maybe because Sandeep and both you are asking, maybe just simply go ahead and flash you the equation. So indeed you will see that it is some equation of this form. This is again you can also obtain from the boundary renormalized holographic action. But indeed, but the thing is that what is hard is O of u. O of u is actually okay. So O of u is not simply the thermal response. So you know the correlation function actually, but you know the correlation. What you know actually is this. Maybe let me again. Yeah. So what you know is actually this correlation function. This is actually never changes, but time reparameterization changes actually the form that which gives a response for u O of u. So actually this is an integral differential equation because so O of u is obtained from J of u by using this retarded correlation function. So although you know gr, but you don't know this T of u, which you have to solve for. So this is what we will see, and so.
But all I was saying
Yeah.
is you can reduce it to a boundary problem.
Yeah. This is exactly it's exactly
You have to
this.
solve that problem.
Yeah. So I'm reducing it to the boundary problem eventually. So simply.
Sorry to be so stupid, but I haven't even understood this. Is that matter in the bulk? How do you reduce it to boundary?
It's very simple. It's just 2D. So
Yeah, I will do it. I'll do it.
eventually, you know, if you take gravity, this gravity is -1 degrees of freedom. Gravity plus 1 matter field has 0 degrees of freedom, which means it's quantum mechanics.
That's the so I thought that matter field was just fine.
That's why.
It's not really matter because it's not really propagating matter.
Number of degrees.
Yeah.
Okay, net positive this is still because the gravity response is still quantum mechanics. I mean, it's still 0 plus 1.
Yeah.
And the entire back reaction. Let's take the matter. Sorry, you should go on. Let's take the matter to be free except for gravity interaction.
Okay.
Gravity-
Minimally coupled.
Yeah.
Another minimally coupled sphere. Okay, go on.
Yeah.
So then don't we have to solve for that minimally coupled?
You can solve for it in the bulk, but because gravity is so simple, in the end, the only dynamics of gravity is that your boundary will fluctuate. Okay.
It's the time reparametrization.
There is a dilaton, but despite that, what the dilaton does is give a cost in action for the extrinsic curvature of the boundary.
And so there's this fluctuating boundary, that's the gravity dilaton sector, and then there's the bulk matter field.
And there's the bulk matter field. The bulk matter field doesn't change the bulk to the AdS2.
Yeah.
So the entire gravity response is what happens is the dilaton responds to the matter. Okay. Now the boundary is defined to be a constant value of dilaton. So where the boundary lies changes in the response to matter. Okay, the extrinsic curvature changes, the action changes. That's the entire effect. So you can understand everything in the bulk.
Yeah. So
One last thing, why is the boundary defined to be a constant value of delta?
That, you know, you have to define the, since the theory has to be defined with a boundary, you have to choose some boundary conditions. This gives a good variation of it. And you could choose other boundary
Yeah.
conditions, that would be another sort of choice.
Grumiller has many papers with it actually. What kind of different boundary conditions? Yeah. So the thing is indeed that everything what you could do can be understood from the point of view of a boundary. The only thing I'm not doing it this way yet because I'm not assuming any specific matter content. If I would have assumed a specific matter content, I would have completely thrown away bulk and talked only in terms of boundary, and I do it a bit deliberately for this reason. So anyway, so far the setup I think is clear. So let me just go on how we go around solving the equations then. So because your metric is always locally AdS2, you can choose this kind of local coordinates.
Did he put boundary conditions as the matter fields?
Yeah, those are the standard ones because the boundary, because the matter is living on AdS2, you just use standard AdS2 holography, and for that there is nothing unusual. So
Do you have, in the way you said it, you took some r goes to infinity limit.
R goes to 0 is the.
So there's no cutoff as well.
Yeah, you can do it in two ways, as Sandeep is saying. You can either put a cutoff or not put a cutoff, and
You put, as always in AdS, you actually put a cutoff, you know, to define holographic quantities, but then you haven't.
take the limit goes to 0. So if you actually don't put the cutoff, you have to be a bit careful about how to define your source, because
Are you going to be using the boundary conditions that Sandeep said, that keep phi constant on the boundary, on the cutoff surface?
exactly. Yeah. So that, but you can do, as Sandeep also said, you can also put other boundary conditions and you can get other results from it. And maybe I can refer to Daniel Grumiller's papers on this subject. I think I don't know if there are other papers also.
No, I don't think so. I think it's more conserved. But at least in that case, you know, the final boundary query is also reversible. Let's put it like this. If it's more complicated, we can talk about it. That the dynamics is entirely due to the fluctuations of the boundary. Exactly what determines the dynamics of the fluctuations can be.
Yeah, it's just clear from what you said, right? The bulk is AdS. So the bulk, the metric is doing nothing. It's all a question of where the boundary is.
Exactly. Very good.
And you know, even though the dilaton varies, the on-shell action continues to not respond to that because it's phi r minus lambda. Okay, so how is the response going to arise? Just from the boundary.
Exactly. From the boundary time reparametrization, actually, that's what we will see.
Is the boundary dynamics easy to write down? Where it's easy to write down?
I mean, if it is minimally coupled, then the equivalence principle can be directly applied, and
Okay, no problem. No, I'm very happy if you interrupt, and yeah, I find new ways to present it. So okay, so then you have the local conservation equations for T mu in these coordinates take this form. Are the fonts coming out nicely? I don't know, with the black on white should work, but hopefully you can read it. So as you see that what I have done, as Sandeep was alluding to, that we put some cutoff. Instead of taking r is equal to 0, we put an epsilon cutoff. And with an epsilon cutoff, you can define, actually, if you put kind of typical matter, irrelevant matter, this, unless you put a cutoff, these equations are not even well defined, so you have to put a cutoff indeed. And then you find this kind of equations for t, z, t, and so this gives you a complete solution of this general equation. So I just need to know what t of tt is. So all the right-hand side is expressed in terms of only a time component, and the other things are, and the other expressions are given here. So this f epsilon and g epsilon, these two functions are functions only of t and not of the z coordinate, of the radial coordinate. So you have only f and g, these are only time dependent functions, depend on the cutoff. So I'm just doing it a bit kind of unusual way, because what Verlin and other people did, they solved the exact problem for conformal matter. So I'm trying to do the analogous thing for general non-conformal matter. And we will see that we just simply get an additional term which they haven't got, but otherwise it's more or less the same. And the solution of dialectron equation of motion is like this. So as you see, the dialectron is not really a propagating field. It's actually it has, first of all, the equation itself is not a scalar equation, it's a tensor equation. And actually two of them actually give constraints. And indeed, you have nothing left after that. And it's simply an equation that tells you that it has 1 over z term and a z term. And in fact, these coefficients satisfy these additional equations, which is simply given in terms of f and g, which I wrote earlier. So f and g was something that we defined in order to get the energy momentum tensor, the solution of the energy momentum tensor. They're defined on the cutoff. And this is something we see here. Now, it turns out that for reasonable matter sector, the radial cutoff epsilon can be taken to 0. So you can actually take the limit where epsilon goes to 0, and you get a finite asymptotic expansion where all the quantities are finite. And the leading term of this asymptotic expansion should be related to the value of phi b, which we have used as a boundary condition. And otherwise, this is the most general solution. And indeed, you can take the limit epsilon goes to 0 here. Equivalently, what we can also do is to consider the boundary to be like, as Sandeep was saying, that you simply conformally map the boundary to something like this, and with some kind of infinitesimal conformal map, and which is given something. This is something like infinitesimal conformal map, and using this infinitesimal conformal map, you can set some boundary conditions there. But if you want to do that, you have to be little bit more careful in the sense that, so j epsilon will not be exactly j of something like z epsilon. It will also have some epsilon dependent term. I forgot exactly what it is, something like this. So you have to be a bit more careful if you want to actually do it this way. So especially if you have like irrelevant matter. So I will not do it this way. I will just simply take the limit epsilon goes to 0, and
you solve for pi in terms of t. And what in the previous page you had a solution for that stress tensor?
The previous page was simply, you cannot completely solve the stress tensor, but you can express tzt and tzz in terms of ttt.
Okay.
Because you have two equations. Yeah.
Okay.
And using that, define this f epsilon g epsilon.
And you're not going to tell us, you'll leave ttt arbitrary?
No. Eventually, I'm going to put some specific matter and solve it.
Okay.
For the moment, I'm just saying how arbitrary solutions look. Is some analogous thing which Polchinski also studied was what happens if you put in conformal matter. I'm just saying the most general answer if you not only, even if you do not have conformal matter, what you can do.
I thought you were in the diagram solution, you have 1 over d and a constant there.
The 1 over z and z, if you just look at the pure NAdS2, you will only have these two terms and nothing else. There is no constant term actually. No, there is no constant. No, there cannot be any constant. One way to see it is that you can, if you just look at the radial equation, it will have two characteristic solutions. One is 1 over z and the other is z. You cannot have a constant term. So if you study just as a radial component of this equation, it will be an ordinary differential equation which involves, it will be something like this. I think phi double prime plus some phi prime and some phi is equal to 0. There is no time dependence, no time derivative here. And the solution will be simply 1 over z and z to this equation. So you cannot have a constant. And then, of course, these extra terms that will appear. And these terms actually, you can think in a way, is renormalizing these constants. It could or may not. Actually, typically, it will not change this alpha, this kind of matter. Actually, I don't completely remember now what happens. But anyway, you will now find, of course, constant. If you add matter, you can find a general expansion can go to all orders in Z. So the general structure could be much more complicated than just simply 1 over Z and Z. Actually, we have worked it out for specific examples. We have worked it out. It's a very long but this is not of much interest how it looks like. Actually, this is okay. So what we can do, we can simply take the limit epsilon goes to 0. And remember what epsilon goes to 0 was. Epsilon goes to 0 was, you simply take the radial cutoff and you can take this epsilon goes to 0 limit. And if you take that, then indeed this becomes the phi b, what the kind of boundary condition you would like to put. If you remember, this is a boundary condition that we put here. So it was phi b. But the thing is that this boundary condition was put in the time du. So we get an extra conversion factor when you convert du to dt, because t is the bulk coordinate and u is the boundary coordinate, boundary time coordinate. So effectively, there will be some extra conversion factor that comes from here. And and essentially, this is nothing but the square root minus h factor that you usually should put. I have not simply put it. So if you put it back, then of course you will get this equation that this alpha naught t of u has to be phi b t prime u. So that simply implements the boundary condition on dilaton. Any question here? This is a very.
And just show me what alpha naught was.
So alpha naught is simply the coefficient here, and it satisfies this equation. So if you put in so basically the equation for nabla has 3 components, and 2 of them are constants. And these 2 are simply the constraint equation, which can only solve at the boundary.
And finally, where alpha naught is equal to phi b times something, or just phi b? Next page.
T prime u. T prime u is the conversion factor from u to t, du to dt, which you have to put in by hand.
When you have matter, there's a possibility of being a constant. Everything is not perfect.
Sorry, can you repeat?
With matter, you have a general function of z now, which depends on your t.
Yeah, it's a general function. Or you can have constant, you can have all constants. In fact, you can even have square root z terms and something in between the 2.
I'm just saying that on the next slide, when you're saying the boundary value just becomes alpha, that won't be true now.
Why?
On the boundary.
No. You can take the limit epsilon goes to 0, then this term will indeed be, if you work it out, in this term will indeed be equal to the boundary condition you want to, the leading asymptotic term will be simply alpha epsilon.
I'm just saying that if I take epsilon going to 0 in this equation, the first term remains, and if there is a constant, that also remains.
Are you worrying that these terms, no, but if you remember the boundary condition, it was simply this, right? It was actually, I should have written z here probably. Yeah, I should have written z. So limit z goes to 0, z phi should be equal to phi bu. So it is simply the most leading behavior of phi that you need to consider here, and nothing more. And alpha and beta so this equation you simply get by solving the radial equation here. So this equation has like 3 components. One is a radial component, RR component, RT component, and TT component. If you simply solve the RR component, you will get this equation. If you solve the other 2 components, these 2 appear as constraints, and they are purely defined on the boundary, and they don't have any R dependence.
I'm very sorry, you said this before, but what was t, little t, this coordinate?
Okay, so it's a very good thing to keep in mind for the entire talk. So t is simply the time in the local AdS2 coordinate.
Okay, and the difference between t and u is because the boundary is equal.
Exactly. So here diffeomorphism carries a cost, as Sandeep was saying.
Because the boundary is defined by phi.
Yeah, exactly.
Even the boundary proper form.
Right?
Even the boundary proper form.
And that's
Yeah.
different from t because the boundary is equal.
Exactly. Yeah, that's why you get this extra conversion factor t prime u. Yeah.
Just to say, at least the situation which, because this might be relevant for your talk, which matter corresponds to an irrelevant mode which is growing at the boundary, if you're doing it in the probe approximation and computing correlators, then you can always impose the boundary phi equal to constant and so on, right? But of course, if you turn on a background for the irrelevant mode,
this is bit.
the asymptotics.
You may
Perhaps what you're trying to do. Then
you will not screw up.
I'm not sure about.
You will not screw up the asymptotics as long as you are considering minimally coupling matter in this range. It works. And the thing is that
That's the kind of thing that you probably looked at.
yeah.
All my remarks were for the
And
scattering
yeah,
process.
scattering. And what we will do, we'll do a bit something audacious, that we will try to solve it exactly non-perturbatively and not by perturbation. So if you, from this actually you will be able to extract, some kind of not OTOC, but you will be able to extract like purely causal 3.4 point or arbitrary higher point functions. Okay, so let's see. So effectively then your equation now okay. So from here, I just simply differentiate this guy 3 times. So here I have not used an equation of motion or anything. It's simply an identity that simply follows from here. It's simply an identity. So to see that, so for example, if you want to, so this dot here actually means differentiation with respect to t. So first if you differentiate with respect to t, then you can differentiate with respect to u first and then add and divide by t prime u. So what I mean to say is that d by du of t prime, d by dt of t prime u will be equal to t double prime u by t prime u, right? And then you can go on and differentiate 2 more times, and then you will get the Schwarzian prime by t prime u square. Okay, so if you do that, you simply get this. And then I can simply substitute this equation here because alpha triple dot, so this was the constraint I got from the bulk equation of motion. I simply substituted here. But you see that if I take the limit epsilon goes to 0, I can simply drop this term because it is simply TZT itself with the 2 derivatives. So I can simply drop this term. If this survives, this should go out. And therefore, I have a much simpler equation, which is that this is the boundary equation. So if you put matter inside, this is how your boundary time will get reparametrized in this form. And this is an equation that one needs to solve. And as you can see, it's a 4th order equation because the Schwarzian itself has 3 time derivatives in it. And you take a prime of the Schwarzian, this is a 4th order equation. And then, of course, and this is related to the fact that you have 3 SL2R charges and also there is 1 constant of choosing the origin of time. So these are the 4 integration constants, the initial value of the 3 SL2R charges, and we will see later. And so it is, so essentially this is equation, and you simply take this. So Polchinski studied this, obtained the Polchinski, Maldacena, they have this equation, except that they don't have this particular term in the equation because they consider only conformal matter. If you have conformal matter, this term doesn't arise, but this is simply the most general expression that you will find if you put in. Okay, so what do we learn is that bulk matter dynamics reparameterize the time at the boundary. So your boundary time becomes T of u, and although it is not obvious as of now, particularly looking at the RHS of the equation, that this equation is invariant under SL2R transformations of T of u. So if you do a fractional linear transformation of T of u, then this equation is invariant. It's not obvious from the right-hand side, but it will be later. And for conformal matter, the second term on RHS is absent, which I already said. Thus, the non-trivial states are distinguished by elements of the diffeomorphism by SL2R. So if you do just an SL2R transformation of T of u, it will give you back the same solution. So it's, and if you actually have no physical effect, all your correlation functions will be SL2R invariant. So because actually you are just simply solving the matter equations in the bulk, so it will be also invariant. And so you will just simply, so the only thing, the solutions are only relevant by diff by SL2R.
So if I ask, so the right-hand side is the contribution of the matter.
Yeah.
And without that, the dynamics that is given by Schwarzian action.
Yeah, yeah,
Right?
yeah.
So Schwarzian action would give the left-hand side equation.
Exactly.
Now suppose I ask, what is the new action for which this is the equation of motion?
It is simply S matter. It's simply the S. So you simply evaluate, you simply do the analogous holographic. So you simply compute the on-shell action of this because G mu is fixed. You can simply compute it and write it as an on-shell action, which is located on the boundary. And so it will be essentially Ju. If you are in Euclidean time, it will be Ju prime divided by the correlation function, U prime, something like that, and you can get it. I mean, you can also get it from an action principle. I'm simply not doing that, but you can, of course, do it. I'll just make a comment on it. Why?
This form seems to be like a probe stuff.
No, it's actually not a probe. You'll see why. Yeah, Gautam, just hold on. I'll come back to it.
Sorry, just to understand about so Schwarzian action means Schwarzian integrated.
Integrated Schwarz. So the left hand side equal to 0 would come from a Schwarzian
Yeah.
function in which is phi b just a constant.
Phi b du
Now,
Schwarzian.
I think
Let me understand that. So the field in that action at T of u.
Yeah,
So a variation of the action would give a functional derivative with respect to T of u.
yeah,
Whereas he's got this prime, which means with the prime is derivative with respect to u.
yeah, yeah. Prime is very
So
respectful.
why are those two the same also? I don't understand that.
What is?
Yeah, it just runs out somehow. Yeah.
Sorry, what's the question?
I'm not saying that this is obviously true, but
So the left-hand side is the variation of the Schwarzian.
Yeah, yeah.
No, it's just that I thought it was the left hand side was a Schwarzian regarded as a function of u differentiated with respect to u. Right? Prime means derivative with respect to u, right?
Yeah, yeah, yeah.
It's not variation of Schwarzian with respect to the field phi. Is it? I don't know.
If you vary with respect to T of u, you happen to get the same equation of motion. It's just simply a long calculation up to total derivative
okay,
terms. Yeah.
understood. Yes, this dynamics demands that the Schwarzian is constant along the.
I see.
It's not.
Yeah, exactly.
It's not obvious.
It's not obvious.
But
Okay,
yeah.
fine.
Yeah, exactly. So
You know, I'm saying the following. So the gravity has become entirely T of u.
yes,
And then there's dilaton become a constant in phi b. And now I thought your matter was entirely given by a data which is T pt of t or T mu u of
no, no.
T u
We will actually have to solve bulk equations of motion to get it. I'm just simply, I just wanted to get this form of the equation. Yeah,
But I'm saying that
it's some sort of universal form irrespective of what matter is inside. So this is why whenever the Schwarz.
but what's your data for the matter? Isn't it just T pt of t or something?
Yeah, yeah,
One
yeah.
single function of t isn't that the additional?
Yes. So equivalently, like you are solving some scalar field in the bulk and getting it. So because it's one, or you can solve one component of TTP.
Why is it a function only of t? Why not a function of the whole bulk?
It's a function of the whole bulk. Yeah,
Or,
it's a function of the whole bulk.
no, in this equation.
In this equation, no. In
I'm
this
saying
equation, no.
What is the Lagrangian?
Hmm.
Which is this is like solving for the back reaction
Hmm.
of the matter.
I think what you can show is that, so what you should do, okay, I have not worked it, it's a very nice question, whether you can work it out that way. More generally, actually, in a specific case, you can, in a specific case, if you just have minimally coupled matter, that's what happens. But in more general case, could be more complicated, but still this form will continue to hold. What you should do is simply construct as matter g mu chi and write it as a boundary term, boundary action. And once you write it as a boundary action,
Which will be non-local, right?
yeah,
Which will be non-local in general.
which will be non-local in general, it will be non-local. And when you vary it with respect to T of u, you will get this term. That has to happen that way.
This term in which this t, etc. Will be determined by the equation of motion.
Exactly.
Non-locally in terms of some t.
Which you will see, yeah, exactly. So I'm coming to that part, yeah. Basically, you're saying everything that I'm going to say. Okay.
Sorry to
yeah.
interrupt, but in perturbation theory you can see that build up, but probably to show this
Yes,
exactly is a little involved. But
very involved, yeah. It's very involved, yeah. It's,
So the first term would be the JJD.
but we know that it has to work out because its bulk equations of motion lead you here. And the constraint, so if you simply use the constraints of the bulk equation of motion, that's equivalent, and that should be implemented by the boundary action, right, whatever it is.
But it could be very complicated if the matter inside is interacting, right?
Yes, it could be interacting, and
that's right.
Yeah.
But I mean, the symmetries are so tight that actually this probably a way just
yeah. So my claim is this is the most general thing that you can have. This is the most general thing that you can have. That's my claim. Okay, so let us see an explicit example. And this is something again stupid and simple. So it is simply a minimally coupled bulk scalar corresponding to delta is equal to 5/4, and with this mass.
Wait, sorry, this most general thing you have will derive, right, for us?
This is the most general thing we derived. Yeah.
This is just true. But
This
now
is
the
true.
complicated thing is what that t is.
Exactly, and this is actually it's a very non-local function of t.
Yeah.
This guy is very
that will
non-local
depend
function of T of
very
U.
complicatedly on what's the matter interaction.
Yeah, and we'll give an explicit form. To get an explicit form, you have to put in some explicit matter and get it.
And I think you are going to assume minimally coupled
Free scalar field, yeah. Minimally coupled free scalar field, yeah.
Those kind of things is trivial to work out. I mean, sorry.
Oh, it's, well, even for that one, that was very hard for us. The reason is that, the reason is very hard because, okay, we'll see why it is hard. Okay, so, when you solve it, of course, you will get this most general expansion.
You must go on a purpose. I mean, for such situations, if the symmetries dictate the coupling to the boundary of the scalar.
Indeed it does, yeah. Indeed it does. The thing is that, of course, so once we look out the full answer, you can of course dig in all the correlation functions like endpoint, but it's extremely hard problem. We will see why it is. It looks very simple, but it's not, because actually what we will see that this is an extremely nonlinear functional of T of U and also non-local functional of T of U, the right hand side.
So that is dictated, though it's not local.
This one because the boundary value of the field transformed under time reparameterization as an operator.
It's like a
of some
correlation
dimension.
function.
Okay, and then you want to couple it to time reparameterization. So, fine. That's all. Yeah.
Okay, so then if you actually study it, study this scale, it looks a very simple form like this. For this specific, so basically you solve the matter once and for all, and if you study what happens on the right hand side, you simply get minus 5 by 4 OT j dot T minus 1 over 4 JT O dot T. And again, it looks very simple, but what's the problem? Well, we'll see what the problem is. Now the time reparameterization equation now becomes this if you put it in back. Put it back and found out what this object is. Yeah, yeah, it's a free minimally coupled scalar field. So you simply get this. Now you have an explicit expression on the right hand side. But what you could do is that you can do some conformal mapping to actually to move it to as a function of U, and that is something that you should do anyway. Not only you can do, but you should do, because J of U is actually the source that experimentalist designs, and you want to compute T of U as a response to it. So that is something.
J and O are what it is.
J and O are simply the usual non-normalizable and the normalizable mode of the bulk scalar field. But the point is that J of T is not yet the source that experimentalist designs, because the U coordinate is the physical coordinate, which is experimentalist time or the lab time. And therefore, you only give J of U, and J of T of U is related to J of U like this. So this is and T of U is the time in the pure ADS, the boundary time of the ADS coordinate, ADS. And O of U will be the response like this. So basically, if you now transport it back, you see that remarkably all the TU dependence goes away, and you simply get something like this. It is simply a function of U. Again, it should be that then, of course, the right hand side, it seems as if it's not independent of T, is completely independent of T of U, but that's not the case. And here comes all the complications, is that, yeah. And O of U is the response the experimentalist actually measures, and J of U is the source that he gives. And if you write this entire object in terms of these physical quantities, T of U completely goes away. But of course, it doesn't go away, it's only hidden. So and the way it is hidden is as follows. Up to here, any more questions? Or?
Sorry, so the J and U appeared in the expansion of TEP, or I forgot. The new scalar.
No, yeah. So it's simply if you compute this object and take the limit epsilon goes to 0, simply compute it on shell and take the limit epsilon goes to 0. Yeah, yeah. It's important that this entire combination is, and it has this nice property that is invariant under conformal mapping. So this object.
Oh, I'm sorry. So G and O were part of the expansion of chi. I mean,
Yeah, for the chi.
Yeah.
And it's a very nice thing that this entire right hand side is invariant under conformal, not invariant, covariant actually up to this T prime Q, and you simply get this vector. Okay, let us see now where the catch lies. The catch lies is that if you impose regularity, O of T of course is not independent of J of T, and you will have a retarded correlation function, and this is a retarded correlation function you can simply get from pure ADS2. However, of course, J of U is the source which is experimentalist part of the system, or use a response measured. So you will actually have this kind of a non-trivial object that you have to actually consider. So the only catch in this equation is that O of U is a functional of T of u, and what kind of a functional is as follows. So it is this functional. So gr is of course a known function of T of u minus T of u1, but T of u itself is not known, and it's a non-local functional of T of u. So that's where the catch lies. Okay, so there are two equations now. So one equation is this basic equation, it's a time reparameterization equation, and the second equation is this equation.
Because Q is determined by what the matter is doing in the
Yeah, yeah. Okay, so therefore, yeah. And now comes the real headache. The real headache is that this equation doesn't, yeah.
Show that previous slide again.
Yeah.
If I were just regarding this as an equation in the boundary theory,
Mm-hmm.
so let's say I'm measuring everything in proper time, u, then T of u, I'm still confused, doesn't appear on your right hand side, right? So what kind of an equation is this? Because Schwarzian T of u is some T with many derivatives with respect to u,
Yeah.
etc., being determined by something entirely, at least, let's say I specify j of u.
So you have to solve the right-hand equation. Yeah.
In other words, just to make sure I understand, suppose I give j of u. That, of course, I can choose to be any function I want, right? How am I going to figure out what O of u is?
Very
That
good.
is what
So
it
this is actually, that is actually, this understanding is the key to solve this problem, because you cannot simply solve this integral differential equation as it stands. The key to map this as a computation in a time-dependent black hole, and we will do that, where the mass is set by the Schwarzian, and with some, so we will derive it. So essentially, it becomes a computation in a consistent time-dependent black
In
hole.
perturbation theory, roughly the fact that this is an operator of some dimension
Yeah.
to leading order determines O of u as a function of j of u.
Yeah.
And then you might try to correct it and so on.
Yeah.
But you are trying to do better.
I'm trying to solve it exactly, and if I try to do
I
that,
just want to understand.
yeah, in fact, if I try to do that, I will automatically face a problem that this object, it doesn't even exist as a Riemann sum. It exists in a sense of integrating distribution. So you have to kind of analytically continue or do some more things to even define this. That can be easily seen, because what happens when u is close to u prime. So when u is close to u prime, so gr T of u minus T of u1, that will always, or u goes to u1, always behaves like u minus u1 to the power minus 2 delta, so it blows up. So no matter what j of u1 you give, this integral will not converge. So it's a very ill-defined integral to begin with, and this is actually so the thing is that this is exactly what makes life very hard. Of course, if you do, yeah,
But sorry,
yeah.
just to understand, am I right that what you would have to do is compute the retarded propagator for this bulk field in the bulk? That's what you have to do, right? The bulk comes in like that, then take its value
Yeah.
towards the boundary to get GRTU
Yeah.
minus TU1.
Exactly. But this retarded propagator is a very simple function in the sense that we already know it once and for all.
Is it a
Free, yeah.
Oh, then you can put it in. Yeah.
It's just that it's a very
The complication is that the shape of the boundary depends on what
But okay, then you're doing a minimally coupled free. Oh, then of course you could at least.
sorry, this is stupid and simple.
No. I really
Actually,
make sure I understand.
yeah,
Then of
yeah.
course it's at least conceptually I think all right. I understand.
and it's still clear that you could solve it in the epsilon expansion.
Yeah.
Epsilon is the
In some.
the J.
Yes, exactly. I think so.
In-
Up to
Because the fluctuation of the boundary is order epsilon square.
the stress tensor.
It's square.
Exactly.
So to leading order you get the free answer, and then
This is exactly the parameter. Yeah. So that's why in perturbation theory I sort of understand.
Yeah, but what we'll do is solve it exactly in non-perturbative way. So yeah, it's almost taking one. Is this actually correct?
no, that's just to scare us people.
12:30.
Yeah, that's all.
So actually,
Slowed you down. No, it's only 12:20.
there's only another seminar I gave which goes actually up to 2 hours. It was in Oxford when Steiner organizes it, and but hopefully I'll.
Easily go to 1. There's no tension.
Okay, then I will be able to one. I won't like to stretch beyond 1. Okay, all right. So, Okay, so basically what first we compute retarded propagator in pure radius. This is a simple function usually, and then given a j of u, we can define O of u using this equation above. Then we have an explicit RHS for the time reparameters equation, and this equation is now therefore integral differential equation of fourth order, because it's there are 3 derivatives in Schwarzian. There's one more derivative here, and the right hand side is an integral involving T of u. It's a non-local object, so we have to solve this now. Okay, so first of all, I just want to make a remark on the SL2R symmetry, is that suppose you define this entire object which appears here in this gr times this times this. This actually is invariant under SL2R transformations, and this is why the entire equation on the left hand side is also invariant. So actually this equation, the integral differential equation which reparameterizes T of u, has SL2R symmetry, is invariant under SL2R transformations of T of u. This is just a remark, and therefore the solutions, so all solutions is basically characterized by diff by SL2R, and these labels are non-trivial states. Okay, so I just quickly go over what's the most general scenario. The more general scenario is this, that if you have matter between 1 delta less than 3/2, I'll tell you why this is important, why to have it within this. If you have, then the Schwarzian is still dominating the low energy response or low energy dynamics, and then you have these two equations. Now instead of 5/4 and 1/4, you have delta and delta minus 1, and you have this O of u will be this complicated, this kind of a functional, and is of T of u. And the retarded propagator is obtained from the regular solution of the Klein-Gordon equation, and this function itself is a well-known function which can be simply solving the Klein-Gordon equation in pure radius 2. If you solve it, you know this retarded correlation function, simply substitute it, and you get a definite equation here.
Your point that you have singularities is true, but presumably I epsilon kind of prescriptions for the retarded should take care of it.
Yeah, except that in principle, but how do you implement it on a computer? If you want to put it on a computer, how do you do it? So that's the whole point here.
So, and again, you said this just to check.
Perturbatively, yes. Yeah.
Conceptually, you could take a particular shape of the boundary, but for that shape of the boundary, find the matter action, plug that in, and then demand the
Iteratively. Iteratively.
No, just, suppose I take a shape. Given a shape, I have a shape. I can then, in terms of that shape, find the matter action.
Yeah.
Right, because I can find out, and then I can check whether this shape now satisfies the differential equation.
Yeah. Then you can also proceed iteratively, except that you do not know whether
what
that.
iteration do you have to do?
Like first, you can solve the Schwarzian, for example, with no matter, then use it to solve it, and iteratively you can proceed
So
like
now
that.
we've got completely boundary action, equation of motion,
Mhm.
and then you can solve it however you want. Right, I've integrated out the matter for a given shape.
Yeah, but it's still this equation that you have to solve, which is, so you're saying that you iteratively solve this equation
just
somehow.
for the shape. Okay, so given the shape, I integrate out the matter. That is a quadratic problem. I can do it. What?
Given T of u, he is integrating out the matter to get O of u. This is this line.
That's exactly. So suppose I know that I have the shape, then I just integrate it out as you say, this line, and then I plug that back in, and I get an equation. Your Schwarzian prime equation is a definite equation just for the shape.
Yeah.
It's a definite, complicated, non-local equation for the shape. That's a definite equation. Then you solve
Except
it.
that it will not solve it, and then you have to.
Yeah.
Yeah. So effectively, we'll do something like you were saying. Yeah.
It's hard to implement
Yeah.
conceptually.
Yeah. So we will probably do something very similar to what you're saying, and then you can say whether we have done it stupidly or not. So, but something very similar actually. Anyway, the point is that we don't consider delta less than 1 because NAdS2 is supposed to be an infrared fixed point, infrared, so it cannot perturb it using relevant operators. And if delta is greater than 3/2, then the leading asymptotic growth of the dilaton becomes larger than 1/z. So you cannot implement the boundary condition, which means the SL2R symmetry of the time reparameter equation disappears along with the Schwarzian on the left hand side. So you completely destroy the Schwarzian action.
Okay, this is what I was worried about. But you say the window up to 3 halves is okay.
Up to 3 halves is okay. And exactly what Sandeep said many times, Sandeep and Gautam, we can also derive the same equations for a normalized on-shell action with the subtlety that it does not easily work with the retarded propagator, and the action is then a boundary effective action with SL2R symmetry.
Just
Yeah. analog of that. Your AdS2 cannot, of course, change because it's pinned to just by the Radon equation.
The model would break down.
The model will break down. Yeah, you cannot define you cannot define the UV cutoff. You cannot define it properly with the cutoff. The theory. Yeah. Okay, so let us see what is the headache. Actually, the headache actually already I said that the equation does not make sense because right hand side is not a Riemann sum. And yeah. Ah. Okay. Okay. Maybe it's not a headache after all. So. Okay. So even if it's
This is the divergence distribution. What's the problem with just finding all this?
Yeah, it's simply that suppose you are doing some integral like this, j of u1 over u1, and if delta is greater than 1, then there is a problem here because
Sorry, that u minus u1 to the power minus 2 delta was about the boundary. What was that?
yeah, boundary to boundary propagator.
Boundary to boundary is for some anomalous equation.
And this equation, unless you do some analytic continuation, this is something you cannot do. But thing is that, as Sandeep says, portatively you can of course make sense of this, except that if you have to now put a t of u instead here, it's very hard to make sense of this on a computer. What kind of prescriptions you will give to make sense of this equation?
So, just to completely understand, what the problem here is what a small e. Where is the problem?
And u equals u1, you'll have a pole, you know.
Worse than a pole, yeah.
You have to sort of try and make sense of this thing.
That happens in ordinary.
And j of u1 is an arbitrary function.
Yes.
Yeah. So you know,
Yeah.
we deal with it in various ways.
Yeah.
Exactly. Except that now this u is replaced by t of u, which causes a problem.
What do you mean, really?
So I have the question. If you have more complicated interactions in the bulk apart from free theory, then how much of that within the classical action is allowed? The statement that everything is on the boundary, this is very classical statement, it's some Green's function statement.
I think he's doing his free theory only because he's using a boundary process.
Free theory is totally
That's all it is.
Yeah.
The worry, at least for me, and I think I understood it very well, is if the dilaton which is obtained as a solution to the equation where the matter is the source, the stress energy tensor of the source, if the dilaton's asymptotic behavior, which is 1 over c or something in your coordinates, if that changes, then you're worried about being able to put boundary conditions like phi equal to constant and so on. So it is no longer a monotonic function.
Yeah. And
that was the relevant part, that
Yeah.
you don't want to go
Yeah.
beyond that so that you don't want to change your boundary condition.
Yeah, but if you have some interacting theory, you have to check whether the interactions might do that.
yeah.
You know?
Yeah,
Right?
in fact, yeah. In fact, even if you put in relevant deformations, and Gautam was mentioning this over tea time, if you put something like relevant operators, but like power of that, like some very high power of that, then also you will have the same problem.
But conceptually, I mean, if he has the same range of delta, then the interactions in the bulk, say there's an overall Newton's constant bulk, the interactions in the bulk will just give you higher powers of G. Right?
It will, yeah.
Perturbation theory,
But after the
everything is
No, but even let's say that his delta is okay. His delta is in this range. But the field in the bulk is self-interacting. That will not change the fact that you still get some equation.
Yeah.
It will be more complicated.
Provided the asymptotics of the dilaton doesn't destroy it.
But how
Yeah.
do we know what the back reaction in the dilaton is?
So,
But that's some UV effect. I mean, at least in ordinary ADS, the interactions don't change.
no, the Schwarzschian itself came from here. The Schwarzschian itself came by implementing this constraint and the boundary condition together.
Suppose in response to this, the dilaton doesn't grow any more monotonically. It goes to a point and then it starts decreasing as you go out.
Oh, why? You're saying because the interactions are so
Yeah,
strong.
I don't know. Maybe the interactions due to the phi's
Yeah.
builds up in the. I don't know.
Yeah, so what happens if you put delta greater than 3/2, it does break down. You don't
Yeah,
assume.
this value of delta is chosen so that the scalar field will first go to its vacuum in the UV. So everything funny will happen in the bulk.
interaction terms, you look at the growth of phi.
Mm.
Then you say if you include the interaction terms, the growth of phi will still.
But order by order could be okay.
Oh, it would be okay.
And your intuition
I think it
about
would be
delta is
perfectly fine.
pretty
I'm
good.
just trying to be careful about perturbation theory versus,
Yes.
that's all.
Yeah.
I thought that was the spirit of your question.
But at least in ordinary ADS-CFT, only delta determines whether something is relevant or not. The interactions above take no note. Unless there's something special about this dimension, I would take the interactions above take note.
But relatively,
No, exactly.
but that might change. If you
It might change in this funny dimension. So in ordinary ADS-CFT, the question of whether the operator is relevant or not is only determined by delta.
You know, it's, first of all, I agree, it's much more sensitive here because the number of dimensions in which energy can dissipate
Yeah, maybe there's something funny.
is none, except that the dilaton mass is actually hidden in the radius of an S2, you know, or something. But it's much smaller. So firstly, it's more delicate. And secondly, all right, order by order, I think we are fine.
Mm.
Yeah, but more than that, right? If you take a field theory and perturb by a relevant operator, then never changes the an exact state. Not in some perturbation theory in the deformation. It's an algae.
But
This dimension I think is very simple.
you must go on, but Shiraz, that's a perturbative statement. If you take a fixed point and you change a little bit, then
No, as an algae flow. As an algae flow that originates in the UV fixed point, then goes wherever you want. But that's the UV behavior. Is that of the conformal field theory? It's just an exact state.
I agree. But now, suppose, I mean, the irrelevant operator is an example, but suppose, you know, even for something which at the quadratic level might have been dying out,
Yeah, can grow over
you
there.
had
Can,
highly nonlinear terms with very big interaction coefficient, and you turned it on a little bit. Now, are we sure of the behavior
No.
in the ultraviolet field?
Let's ask, I'm sorry. Let's ask about a quantum field.
Yeah.
Say we have a quantum field theory, there's a fixed point and there's an operator spectrum with a relevant operator. The algae flow seeded by it in the UV is the fixed point. That's an exact state.
Yes.
Then it goes wherever it goes. That must translate.
here is an infrared fixed point. So if you are seeded by infrared operator, the UV is not well defined.
3/2 is the analog thing of perturbing by a relevant operator.
Okay, we should do this over lunch.
Okay.
But Shiraz, even there.
It's a good to continue over lunch with.
If you took that operator and then turn it on about the, take a fixed UV cutoff. Okay, fixed UV cutoff, and then turn it on with some strength for a given cutoff. See, I'm not sure what will happen.
That's a different question. I agree.
That's the analog of
Analog
having
of,
the
yeah.
boundary somewhere.
The UV is ill-defined here, actually. If you
Okay, now you may say for any value move it, yeah. So, okay, those are two different things, but
Yeah, yeah.
here move it is not so easy because move it is vis-a-vis the fixed value of the dilaton. See, the boundary, this is the point, second point. The boundary
You're
is more
effectively
subtle.
working at finite cutoff.
Yeah,
Yeah.
yeah,
That's now.
boundary is more subtle, so. Okay. all
Yeah,
right.
I know.
Anyway, all right.
Mhm.
So this is a very interesting case of ADS.
So it's
Yeah.
different. You're saying it's different.
yeah, it's different from the usual setup. And also the thing is that, just want to make another remark, is that T of u actually not only depends quadratically on J of u, but actually quartically and also higher orders, because it's not simply a quadratic dependence on J of u. T of u has very higher order dependence. If you try to perturb around a thermal background,
I saw this before. What happens with the Wilson constant? I mean, the right-hand side is multiplied by Newton's constant, isn't it?
yeah, I just simply, so, okay, so I will,
Not just a question of, I mean, I think it's there.
it's there, but it's simply the way I have put it. I just put the whole Newton thing outside of it. So that's,
So I'm just,
Maybe I
I'm
should.
just asking about back reaction. So if you have,
yeah, in principle it should be there. Yeah, it should be. There should be a Newton constant over the whole thing if you want to normalize it in usual way. But
Allow me to say, if you think of this as n square, you typically want to
yeah, exactly. I usually do that
Or
way.
if you do an S-wave reduction, then you get 1 over G Newton outside the whole.
yes,
This is what I did. Yeah.
So it's a sort of natural thing to do, and then you
Mm.
control, if you want to control in perturbation, you control in the stress.
Hmm.
Just relate to what you just what you're going to say.
Okay, so maybe now I can go back to, again, this I think I'll just go over quickly because I think everybody knows it here. Not everybody, I think, but like, okay, nevertheless, let's see. So if you, in absence of matter, we simply have this equation that the Schwarzian has to be a constant and could be both positive and negative constant. Now, I can always choose it to be something like this, 2 pi squared by beta square, and beta will have some interpretation which we will see. So for the positive sign, the solution turns up to an SL2 transformation of T of u. It is simply tan h of pi u by beta. So that's how it turns up. So beta is a parameter, and then there are 3 SL2R parameters. So this is how the most general solution will look like. You can also shift u by some constant if you like, u to u minus u naught, that also will work. Okay, so this is the most general solution that you can find, which has four integration constants actually hidden here. And for the negative sign, the solution is this. So actually but because this is a periodic function, you will say it's unphysical. So essentially only h greater than 0, a Schwarzian greater than 0 will make sense. But this is true in the Lorentzian case. But if you have the Euclidean case, actually the sign of the Schwarzian changes. Because what the Schwarzian is like this, t triple prime by t prime. So if you take t goes to I tau, it, and u goes to iu, the sign actually will change. So now what was unphysical will become physical, and what is physical will become unphysical. So that's the way it works. And then, of course, this beta will be related to the periodicity of the time circle. Actually, I have done something really bad here. I should have written it 2 pi u by beta, then beta would have been indeed the temperature, in inverse temperature. Yeah, but somehow I didn't do it, and I'm sorry about it, but I did it for, yeah, up to a factor of 2, it is actually the periodicity after Euclidean continuation. So to understand what it physically means, sorry, you can simply, it is? Okay. Yeah, it's not so important for this, for what I'm saying. So you have this now solution, and if you do the following transformations of coordinates, you will simply go from this pure ADS patch to this ADS2 black hole with this particular mass 4 pi by beta square, where beta is now the parameter of transformation. But crucially, you see that you have reparameterized the time at the boundary. So although these two are the same solution, at the time, at the boundary, that this time is not the same as that time. So t and tau are not the same times at the boundary. So to see that, you simply, of course, take the boundary. Boundary will be simply z is equal to r is equal to 0. And as z is equal to r is equal to 0, t and tau are related like this. So t will be equal to tan h pi tau by beta, and that's exactly what we want. And the mass will be then minus twice the Schwarzian. So the mass is determined by the Schwarzian. So identifying now tau with u will imply the time reparameterization where the Schwarzian is negative and constant produces a black hole solution. So basically what is happening here is that if you look at this solution of the Schwarzian is equal to constant, this from the bulk point of view, it will simply an ADS2 black hole with the mass specified by beta, 2 pi square by beta square. That's a simple statement, okay? The mass is positive. Okay, so I thought this will be really very well known. So, but again, a simple caveat thing is that not all coordinate transformations will reparameterize time. In fact, corresponding to a boundary time reparameterization, there can be many bulk coordinates. So for example, if you do the simple change of coordinates, the boundary is at rho is equal to r is equal to 0, but you see v is equal to tau at r is equal to 0, so it doesn't reparameterize that term. It simply changes the metric to this Eddington-Finkelstein form, which is often more useful. So this is simply a remark, which is okay. So now we come to the constructing time-dependent solutions. So what is quite useful to do, as Sandeep remarked, I think, in between. So we have to understand exactly what bulk computation we are doing to extract O of u, and this will actually help us to give meaning to this apparently meaningless equation. So we will try to do that. So for that, what I'm going to do, I'm going to first of all make a simple remark that if you reparameterize t of u by tau of u, so instead, so tau of u, so u takes from the lap time to the ADS time, but tau of u will take from the lap time to the time of our ADS black hole with mass 2 pi square by beta square. Is the statement clear? So instead of taking, so instead of t of u, if I define a new variable tau of u, the physical meaning of tau of u is that you go from the lap time to the time of a ADS2 black hole with a fixed mass, 2 pi square by beta square. And then the Schwarzian will transform in this way. There will be an extra term. It looks a bit different with this extra factor of 2 pi square by beta square. Okay, so now as a warm-up, we can try to understand what happens if we further reparameterize time. So suppose we now start with this Eddington-Finkelstein-like coordinates. Here again I call tau instead of v just for reasons of convenience. So it's still tau because v is equal to tau at the boundary. I'll simply call it tau then. Yeah.
I'm sorry. So you're using something that again I should know, but global ADS2 and the black hole are the same space, locally or globally?
Locally they are same, but globally the time at the boundary are not the same. So the diffeomorphism is non-trivial at the boundary.
Basically, black hole is global ADS2 is identical.
And these identifications survive on the boundary?
Are you making it clear that?
Yeah, that is of course in Euclidean coordinates. In the Poincare patch it is like this. And then the black hole will be a smaller patch inside this Poincare patch.
So again it's some identification?
No identification here. It's simply a smaller patch. The black hole coordinates will simply cover a smaller patch of the global coordinates.
That is in Minkowski.
Yeah, in Minkowski, because now I'm in Minkowski now.
So you just take part of global ADS2 and that is the black hole.
Yeah. Well, one way to easily see it is that simply look at the solutions for the light cones, where the light cones get mapped to, and that easily from that you can figure out that.
Is there a singularity in these black holes?
No. There is no singularity.
So you analytically continue the black hole, there's no R equals 0 singularity?
But you know what happens is if you take this linear dilaton solution, which you need to control the back reaction. You can't take the dilaton to be constant because there's no, then the energy back reaction goes away. Then as you go inward, you begin to get more and more negative. So if to begin with, you know, this value of the dilaton is the value above the horizon radius of the S2. At some point the horizon radius becomes 0. And you should morally regard that as a
Singularity.
singularity. You won't see it much in the 2D truncation.
Yeah. Thanks for the comment. Yeah. It's very useful comment. Okay, so actually, Sandeep, maybe you can make a comment later when we get when we get to the answer. We see okay. So maybe we come back to this issue later.
But just on the maximal angular continuation of the black hole is just global.
Yeah, exactly. Yeah, that's the best way to put it. Okay, so as a warm-up, what you can do is that you can simply look at this m is equal to 1 black hole, where beta is equal to 2 pi or m is equal to 1. Yeah, and then what we do is we do these particular transformations. The useful thing about considering the Eddington-Finkelstein coordinates is that you see that if I want to go from one Eddington-Finkelstein coordinate to another Eddington-Finkelstein coordinate, I only need to do the time reparameterization doesn't mix with the radial reparameterization. And essentially the rho is that this is actually a time-dependent SL2R transformation of R. If you do this, magically you go back to the Eddington-Finkelstein coordinates. It's the same metric except that you have a mass, time-dependent mass.
This is an example of the general technology found by Roberts.
Roberts.
This is the Roberts transformation, which
Really?
I mean done in one higher dimension, but in the asymptotically ADS2 solution, it's given in terms of some Schwarzian formula. You know, so what you have given here is part of that story.
I didn't know that actually.
Yeah, so you have this Madras class of metric, which has been
I thought.
asymptotically ADS3 metric. Now for asymptotical ADS2, you have the same Madras form, and you have from Poincare, you can come to any one of them. And the example that you have just given in terms of rho and r in the next thing, it's a Roberts transform.
I didn't know this at all. So maybe you can give us a reference, so we have to cite it.
I mean, we have used this in my paper in Pandora.
Really? Okay, we thought that we found it for the first time. But anyway. So then m of u will be given by this equation. And so m of u is basically twice of the Schwarzian of the ADS time. And if you write this twice of Schwarzian of ADS time in terms of tau of u, it will be like this. So essentially m of u, so the moral part is that with corresponding to any tau of u, you can actually associate a time-dependent black hole where the mass of the black hole is essentially twice of the Schwarzian of tan h tau of u by 2. So this is the moral of the story. And obviously one can make a simple check that when m of u is 1, that is beta is equal to 2 pi, then tau of u is a solution up to SL2R transformation, because if tau of u is equal to u, the Schwarzian vanishes and you simply have 1. So twice into half is 1 and m of u becomes 1. So exactly that is in a solution.
Just to make sure, it's a black hole, but with the mass being time dependent.
With time dependent.
So presumably you're throwing in stuff,
Mm-hmm.
and then this is back again.
Yeah, we will see that. This is simply a physical interpretation of the fact that what means a time reparameterization. So suppose you have done an arbitrary time reparameterization of tau of u, you can map it to a black hole. That's all I'm saying. Yeah. Okay, now we will exploit Ward identities. So first is that the conservation of energy, and the general equation for conservation of energy will be simply this. That's something easy to show. I mean, that is general fact of quantum mechanics. Now its existence originates from the transition symmetry of the Lagrangian in U. So it has nothing to do with the T transformations. The time reparameterization, now the time reparameterization equation can be written in this way, that you see that what I've done is, if you go back to the time reparameterization equation, which is here, maybe I should write the more general form, that is useful. So this, I can pull something on the right hand side if this O j prime u, and then I get a delta minus 1 plus O j prime u, and this becomes total derivative, which I can pull to the left hand side. I said phi b is equal to 1, just for sake of convenience, and then I simply get this equation now, that is, if h of u is defined like this, then this is indeed the time reparameterization equation, only written in this way. Now tau of u is the boundary time reparameter that takes 1 from lap time to the time of m is equal to 1, beta is equal to 2 pi black hole. So that is the interpretation. But okay, so now what is happening is that you have actually 3 SL2R charges. If the equation was simply Schwarzian is equal to constant, then actually there would have been 3 charges which have also been constant, and these are these charges. So for sake of time, I didn't put it on the slides what kind of transformations they generate. You can explicitly find them out. And so there are these three conserved charges. And now what we have done, we have derived the Ward identities in presence of matter. In presence of matter, the Ward identities are this. So instead of just having right-hand side 0, you will get something on the right-hand side. You can get it from the action, or you can do it in many other ways. Or you can explicitly get it from the equations of motion also. It's the easier thing to do. And so these are the 3 Ward identities that you will get. And these actually are simply consequences also of the equation of motion, which is this h prime u is equal to ou j prime u. So these are so you have these Ward identities in presence of matter. Now what you can also show that the Schwarzian is actually the Casimir. Minus twice the Schwarzian is the Casimir. So the Casimir is actually the black hole mass in the dual geometry, which is actually time dependent. And the Ward identity for h of u is not independent of the 3 SL2R identities, because once you put in these 3 Ward identities, the Ward identities for the h of u will simply follow from these 3. However, it is useful in the sense that it provides a numerical check while implementing our algorithm. Commutes, yeah, it's a Casimir, yeah. What do you mean by commute? We are,
before it was a Casimir. So when we saw that this equation has this symmetry, SL2R symmetry, I know that I have these three generators, all of which annihilate this Schwarzian. So then it must be either the Casimir, it must be one of the
Sorry, it's a comment or a question? It's a comment or a question?
I'm asking, is it not that if you have three charges, all of them commute, so must be on the, it must be a fragmentation?
Okay, I take it as a comment. Okay, let me move on because. Okay, so the algorithm is as follows: that what you do is, I suppose that a system is thermal initially, that is beta is equal to 2 pi. I can choose whatever initial temperature I like without any difficulty, because simply, yeah, it's simply a kind of, after all, it's a conformal system in some way, and you can choose initial temperature whatever you like up to some. It simply fixes the units. So we can surely choose the SL2R frame also in this way that, so in that case, the solution of the Schwarzian is simply, so remember that our solution was tan h, so T of u was equal to tan h pi by beta tau of u. And therefore tau of u will be equal to simply u. If tau of u is equal to u, if tau of u was equal to u, then we had a thermal solution. So initially, suppose there is no perturbation, you can start from a thermal solution. So you take tau of u to be u, as simple as that. And in that case, but this is only up to a choice of an SL2R frame, because you can do a SL2R transformation of T of u and you get more complicated tau of u. So we can choose SL2R frames such that tau prime is equal to 1, that is tau of u is equal to u, and these other higher derivatives vanish. And this simply tells you that you have chosen these values of the SL2R charges, initial values, where h of u is half. H of u initially is half. So in the far past, the source j of u also vanishes. So this is simply the initial conditions for my taus.
So you start with a black hole at some finite temperature, no source term.
No source term. And then, of course, the source will be turned on. The experimentalist gives a fixed profile for j of u, which is simply turned on. And the initial condition for tau itself merely chooses the origin of tau time, so it's irrelevant. Has no physical consequences. So what the physical consequences that we, so you can always choose this kind of initial conditions if you start with the initial thermal, which I exactly mentioned.
Just to make sure,
Yeah.
are you doing it in Euclidean or
Minkowski,
Minkowski?
everything is in Minkowski.
And so do you have to assume some boundary, at least if you're doing the single boundary, you have to assume something about the state here, that is, from the past horizon also stuff can come out, right?
Yeah.
To compute the response.
So what I will do, I will have a completely retarded and causal evolution.
Completely retarded.
Evolution. So I will only use a retarded correlation function. So. But in the general solutions could be very, very interesting to find. Yeah, that's very, very good point. Yeah. So suppose we know, now the thing is that now I can easily tell you an algorithm what we can do. So suppose we know how to upgrade O of u at each time instant, then we can actually solve the time repairment as an equation just exploiting Ward identities. So let us see how it works. So suppose we know how to upgrade O of u, I can simply integrate the three sides and update q0, q minus, q plus. Is this clear? Suppose I know how to integrate, update O of u, I can update q0, q minus, q plus. If I know how to update q0, q plus, q minus, I can simply use the definitions of q0, q minus, q plus to compute tau prime, tau double prime, tau triple prime. And tau of u I can update by simply knowing tau prime u at the previous instant. Okay? So if I know how to update O of u, I can easily use the SL2, the Ward identities to compute tau prime, tau double prime using simply algebraic methods. Okay, so that's one thing. But then of course, I have to tell you how do I upgrade O of u. The way I upgrade O of u is that we know that tau of u is physically the time of the ADS black hole with m is equal to 1, and we can simply obtain it by solving the KG equation in this fixed geometry in a causal way. So initially, of course, the scalar field vanishes, but you have to be careful. The thermal source that you have to put in this black hole is different from the actual source which the experimentalist presents. At a given instant of time is given by tau prime of u, this extra factor. And then, but when I put this source, I can simply solve the Klein-Gordon equation using method of characteristics, a la Chester-Yaffe or whatever. I mean, that will be an overkill because it's simply solving a Klein-Gordon equation. And then obtain the response, and this is the OH tau that we get as a response, and from here we extract O of u. So J of u is the input, then from there we obtain JTH, and from JTH we obtain OTH, and from OTH we obtain OU. So this is how we upgrade O of u at every time instant. And now we know how to do that, so the algorithm is complete, and the evolution of tau of u and the state is fully causal.
So at the initial time, you know what's going on. So you solve a little bit, and then you see how the boundary changes a little bit. So you know how your tau of u has changed, and then keep going.
Yeah, it basically is a purely causal evolution now. It's a completely causal evolution. So the thing is that this is how we do it. So now, because now we have gone through all the pain and strife, let us now simply enjoy the results.
Or are you doing the polynomials? Okay, in some strain, etc., it's basically the mass n equals 1 black hole.
Yeah.
Solve the Klein-Gaussian equation of the field, but then you have to solve for the dilettante, right, to know where the boundary is.
Well, no, I don't need to do that because.
The charges allow you to get around.
The main point is as follows. Actually, the main point is that once I write the time repermutation equation, I don't really need to know where the boundary is, because the boundary is actually equals to the bound. Yeah, T of u and z is equal to epsilon. The boundary is a z is equal to epsilon t prime u. If you want to put it back in that language. So first of all, you know tau of u. From tau of u, you know T of u, and then you can know the boundary in ADS space. If you want to do that way.
You just need to know that O of u and O of u you find causal.
Yeah, causally.
You know the Grimm's function everywhere, because you need to know your shape.
Each of them is third.
At the initial time you know it.
Sorry, each of them is third derivative. No. These equations by themselves are just first derivative.
Yeah. And we know that there's no J initial. So then you first have the J, then
Suppose you have a fourth derivative equation of motion.
Yeah.
And you have a first integral from that. Then you will have one third derivative constant. Okay, not three first derivative constants. You have three.
Yeah.
Sorry.
Just
You have
conceptually
three constants. Each
Yeah.
of them is third derivative. So there must be some redundancy here. Like q plus and q minus, okay, are not really constants. I mean, they are redundant somehow.
No, actually, if you suppose you know tau, then to determine tau prime, tau double prime, tau triple prime, you need all the three charges. Just knowing two of them is not good enough. They're algebraically independent.
Yeah, I'm just saying, just from the point of view of differential equation, a fourth order equation, differential equation, if it has a constant, it
Has a
will
constant.
be-
No, it's not a constant. So the fourth order, there is no constant here because the h of u is not conserved. You have h of u prime is equal to ou j prime u. So it's not really conserved.
Yeah, maybe I can ask you later.
Yeah.
I mean, I'm saying that take any of these charges which have three derivatives and say that their prime is equal to 0. So that will give you a fourth order equation.
Yeah, then that will be equivalent to the Schwarzian equation actually.
And then you have the q minus and q plus.
So all the three equations are not independent of each other in that case. They will be the same equation.
Therefore, only q0 perhaps.
Yeah. So in the absence of matter, in fact, even in the presence of matter, each of these equations are actually not independent of each other. If you each equation individually is simply the time repermutation equation itself. It's just that you are doing it this way because if you know the three SL2R charges, you can extract tau prime, tau double prime, tau triple prime, because algebraically these objects are independent of each other. And this helps you, if you know how to update the SL2R charges, you will be able to solve algebraic equations and extract tau double prime, tau triple prime, and tau prime. And the advantage is that here you are solving only first order equations instead of solving like higher order equations. So you have converted it to a simple algebraic problem essentially in this methodology. Yes, I mean the warranties are modified. I mean, see, in presence of matter you will have a modification of the warranty because if you put in j of u, which is time dependent, it will break your time transition symmetry, but then there will be a specific right hand term that you can derive, right? So yes. So similarly here, so you break the SL2R charges just like you break your time transition symmetry, but the right hand side is fixed, what appears.
Sorry, just to make sure. So you are going to solve it numerically.
Numerically now, because otherwise that there is no hope. Yeah. Okay, so So now we see now we can enjoy the results. So first let me show you what happens if you put a fixed j of u. So this is something that experimentalists give, say a Gaussian. I would rather like this off here. And then O of u will be a function of u. I'm really sorry about these plots because there is no labels for the x-axis, y-axis.
And as a comparison, something to think about, you could look at a Vaidya metric, right?
It is a Vaidya metric, yeah.
Is it completely Vaidya?
For massless.
So this is exactly a Vaidya metric. So once you reparameterize time, it becomes a Vaidya metric.
It becomes a Vaidya metric, and this m of u, then the question is, how is this m of u related to your j?
Well, so m of u is related to tau of u, and tau of u is related to j in a complicated way.
In a complicated way. But,
Yeah.
but I'm saying that, in some limit, there's some simple relationship between the energy input, presumably, and this change in m of u.
Yeah, in the perturbative limit, you can simply probably obtain from this simple water entity by using O of u will be simply the linear response.
Well, see, what I'm saying is that you send a wave in, there's some back reaction, some of it goes in and some of it comes out. To the extent that nothing comes out, nothing's reflected, it's a very simple geometry, right? So whatever you send in goes in. But presumably the complications are because there's some tuck. Do you see that?
Yeah. But here, actually, we don't have to really solve these things in a. Yeah.
I mean, you just solve it. I know,
We
but-
just solve it. We don't actually solve the equation in this particular
I'll
geometry.
make my question precise. Suppose you turn off j after a certain time.
That's what we did here, actually.
Okay, then how long does the metric take to settle down?
You'll see the plots. Okay. So this is this is actually O of u. So actually this is so it goes from 0 and then wiggles up and down. So I'm really sorry about these plots, and also I see that it actually is a parallel line, but because this is a curvature, it looks non-trivial reparameterization of the original input. So.
Wait, the linearized equation of motion of your minimally coupled matter field time in your black hole background, does it have quasi-normal mode?
Yeah, it has a quasi-normal mode, but
Or many?
many. But the thing is that unlike there's a difference from higher dimensional analogues is that they don't have oscillating real parts. They only have
But
pure.
there's an infinite number of quasi-normals.
Yeah,
So these will be excited.
these will be excited. Yeah.
Okay.
Yeah.
Yeah.
In and out.
Yeah. So in quasi-normal mode in ADS setting, you turn the source off. If you've excited it, then you turn the source off. What remains after that time is quasi-normal mode. So this is just slowly.
We had this extensive discussion. S-wave,
S-wave.
But this is not the chi.
Oh, just for the guy.
Yeah.
This is just for the chi field. Yeah.
Sure, of course. Yes.
Okay, so this is how H of u looks, and this is what is the most amazing thing. Normally, if you do work on a higher dimensional black hole and you solve an explicit quench problem, which we have done with Lata and many other people have done it. And so if you want to do it, you will see that the black hole mass always increases, never decreases. And that has to do with the fact that the spectral function, at least the linear response theory, has a very particular behavior, which is omega rho omega. So the work done on the black hole is essentially this, that j omega square times omega rho omega. And you can show that this omega rho omega is always positive definite if it's a bosonic correlation function, which means the work done always has to be positive. But this uses linear response theory. But it turns out that at least for a higher dimensional black hole, the qualitative answer that you get from linear response theory actually matches the true answer to a very good extent. But here it's a rather surprise.
What is the thing? I mean, you expect physically to only be able to dump stuff in, not for stuff to
Exactly.
come out.
Yeah, so the thing is that this, when we do the exact computation with Lata and others, or Chesler, Fa, or all of them, so what you do is that you actually solve both the geometry and the scalar field together in this using method of numerical relativity and method of characteristics. And if you just use the linear response theory itself, you will see that the mass can only increase because, as you say, things can only go in, nothing can come out. So of course, you can only dump. So the black hole acts like an energy dump. But here it acts like a pump rather than a dump. That sounds really strange, and when extremely strange, and this is what
What do you mean here itself? Here it acts like, meaning in the nonlinear.
in the nonlinear situation for NAdS2, that's extremely strange, and that is why
You're saying linearly, a small
is absorbs, yeah.
But when you take the perturbation very large, it can.
It actually now completely changes its behavior. And this is something when Lata first showed me, I completely told her it's complete nonsense. It doesn't simply, your code doesn't make sense. But actually then Lata actually fought with us and convinced us that actually this is correct. And indeed it seems to be correct because one of the way you can check the code is that you can independently check this word identity. Whether,
Yeah, that's what I'm wondering.
well,
The
yeah.
analog of area here is the value of the delta, which in the ground state is then fixed by the mass.
Right. So if the mass
Yeah.
decreases, doesn't it violate the area increase theorem?
So I think that is what is happening. I think this is where the whole catch lies, is that if you think of it now as some kind of lower dimensional version of a higher dimensional theory, I think you cannot simply choose phi b to be independent of j of u. The boundary value of the dilaton should not be independent of. So here we have in principle we have two sources, and this is something that we have frozen to be phi b, but in reality this is actually should be also functional of g of u. That depends on how your NAdS2 is embedded in higher dimensions.
At least in perturbation theory, I can guarantee you can do this, because you can look at the full Fourier equation and show that you get the same response.
Yeah, area increase theorem is a theorem of the solutions of general relativity. It doesn't say anything about the local solution theorem near the horizon.
Yeah.
Doesn't say anything about the boundary condition.
Yeah, so here of course there is no dynamical metric. The metric has no dynamics.
Fine. It seems to me that the area, this dimension puzzles. I mean, I don't have intuition for this dimension.
Unless, yes, suppose we would be able to derive some area
Increase theorem. Then as long as you've got a solution, which is a solution near the horizon, area increase theorem should apply.
Yeah. So the thing of course is that, okay, the thing is that, well, usually the intuition is that once you put in things inside, the black hole mass would grow, right? But that assumes, of course, there's a back reaction. But here there is really no back.
It's a theorem because the area increase.
But that requires.
The only input is some energy conditions on the.
Can you do it for the apparent horizon, locally as the thing goes by?
The area, is there an area increase theorem for the apparent horizon? There are some things.
There are some analogous
But
things
for
here.
the final causal there is,
They're
right?
different.
So we can just, take the S-wave version
Yeah.
of that, and as long as the matter will satisfy whatever energy conditions, I think phi has to increase monotonically.
You mean the dilaton?
Yeah. Just apply it initially and finally or whatever.
Yeah, that's what I would have guessed.
Yeah, this is actually came as a big surprise to us, and we don't understand this. I don't know why it could be that the code is completely incorrect, although the principle is correct. The thing is that as I said, we checked the code like this. We actually checked whether this word identity is actually also satisfied, this h of u word identity, because that's not part of the code. But we also checked whether this is satisfied. This h prime u is equal to ou j prime u, which is completely different from this other three. But anyway, so it seems like the code has kind of correct.
That's how area increase theorem can be.
It does settle down, so the final h becomes a constant once the source disappears, but it's simply a lower value than the original value that you started.
It settles down. Then can't you, I mean, I think you could probably just run the Hawking's argument on the setup
Hmm?
and see what's going wrong with the algorithm, unless the dimension.
Yeah, I think one of the things that the Raychaudhuri equations and everything uses is this divergence of your null geodesics, right? But here there is the null. So then, okay. So first of all, what the area increase theorem comes like this. You have the theta of the null geodesics. The theta is simply the divergence of null geodesics that generate the horizon. But here there is no divergence of null geodesics to begin with, because there is only one line, and so I don't know how to even run that argument. So.
I mean, at least in the old days when many people studied 2D black holes and so on, there are versions of area. Very closely tied to this.
Well, first of all, there is no area here probably.
No, value of the dilaton is the area. Okay? That's what happens in the S-wave, and you can prove it in two. In a very similar way for many situations. I have not done it for GFT.
Okay.
But for CGHS and analog S-wave reductions, literally, not near extremum, you can have it.
Well, it could be that what you are saying is correct and what I'm saying is also correct, because simply because we have not computed the value of dilaton on the horizon. I mean, so we have not computed dilaton exactly in the bulk at all. And if we do that, maybe what you are saying will be still correct, and also my result will still be correct. it could be a very interesting calculation to do. So thanks for your comment. Yeah, it's very.
That's fine.
Yeah.
The value of the kilogram at the horizon is fixed by the mass.
Exactly. You are saying the mass decreases. So you wait long enough, nothing funny is happening. It looks like it's violating something.
Yeah, this is what I want to understand.
So, all right, but okay, so it's an interesting, okay, we should try to prove it for J2. I mean, I haven't done it, but that's it.
Yeah, so this is a solution of the dilaton that we found, right? And you are saying somehow at the horizon it should be exactly constant? This, what you mean by?
Usually the value of the dilaton should increase, corresponding to the mass at the horizon.
Yeah, we have to do this computation. That's interesting.
In the middle, funny things can happen. When you take it very early on and very late, you've got.
Well, in the very late time, it does seem to increase only. I don't know.
No, but compared to the very early level.
No,
It
no.
settles down, right?
It settles down, but
It settles down to a lower value. That's your point.
yeah, at the very late time, it does seem to increase and again stabilize.
In fact, for SD, what I recall is there is a little stronger version because at root, okay, you have Burkhoff's theorem, you throw in a shell, right? The Burkhoff's theorem inside it, Burkhoff's theorem outside will match. The shell has positive mass, the horizon moves out. So that's why there's actually a local version.
You know, all these funny things about energy and so on go away.
They don't happen.
Yeah.
Okay, now here
But
you
is
have
there a
mass.
reference where people have actually worked out this for? No, I will be
We
happy
have to
to.
prove it, but
Go on.
Sorry, so what happens if you not look at h of u but h of tau or h of t?
That's a good question. We haven't. I cannot tell you offhand. It's a very good question. Probably, yeah. That might actually monotonically increase.
No, but U and type T, everything becomes sort of proportional to everything else when everything is settled down. Right? Very late time, very early time. Just a question: is the mass smaller or greater? Is the final mass smaller or greater?
We find it smaller, and that's where the whole puzzle is.
But you know that not redshifted, right? You may just be measuring energy from a different moving frame. I mean, like, different that. The
Yeah.
molecule is moving. So you're just measuring it from a funny frame.
That's a very nice comment. Yeah, that's a very nice comment. It's exactly something like that. So, yeah, I think it is exactly something like that. We will see in the next example. Yeah, you are actually right there.
See, actually,
Yeah.
this is a good comment. I've been worried about your statement that U is the coordinate that the experiment.
Yeah, it's true. It's true.
No, but I'm worried about it because, in a situation where ADS2 emerges out of ADS4, the Poincaré time of ADS2 is related to the asymptotic ADS4 time, not the proper time along.
Yeah,
with
yeah.
it. So, anyway, okay, you have to measure mass. All right, let me not get into that. You have to measure mass in a careful way.
Yeah. So here I'm simply using the water energy to define mass. So here what I'm doing is something really simple and stupid in the sense that I'm simply using this water entity to define H of U because this is something that we know is a general water entity.
I understand. So I'm just saying there is a well-defined notion of mass, which I have to make sure is, how it's related to H. Yeah, exactly. An ADM, more like an ADM kind of. So that.
The Polchinski and Maldassina claim the Swarzschian is the general ADM
is the
mass.
general
ADM
notion.
mass, yeah.
And that's what you are using as your H.
Yeah. Well, we don't have to necessarily use it. We simply use it because it matches with the water entity.
And you're using comparing Schwarzschild at the place on the boundary where phi remains fixed.
Yeah. At the cutoff. Yeah. Okay. So this is what we do. And the interesting thing is that if the source is extremely large, then H of U can even become negative. And I have absolutely no idea what it means, whether ADS has to fragment or, because what happens if your mass becomes negative, you open up a new boundary. It's like dumping energy to the other side. It could be interesting to figure out. So what we did is as follows. So this is something I'll just skip because I want to finish in 5 minutes. So, so what we did was, okay, so I want to finish really in 5 minutes, so I don't want to hold up your time more. So what we did was as follows. So what we did, we tried to make the source dynamical and tried to couple it to a dynamical source and find out what happens. So in that case, the source J of U is identified with X of U. So we got a bit of inspiration from this kind of things, which I think Rohan and Arnab and the paper they have written. So they think that the NAdS2 can emerge on the wall sheet, and the wall sheet probably indeed you can freeze the phi b because it simply your string may not extend in those extra directions. And x of u simply could be one of the spatial coordinate, and you can use it as a source and think of it as coupling to some kind of an operator with a linear coupling. So essentially in that case, O of u can be interpreted, so this is a potential, O of u lambda x of u, and this can be interpreted as some kind of self-consistent string tension. We have a confining potential somehow, and this essentially the idea is to somehow implement it some kind of semi-holographic version of a confining, like a di-quark or some kind of quarkonia in quark-gluon plasma medium. So you have a similar situation where d2 xu du2 is minus lambda x2, and then from here it follows that this is the equation of the energy conservation of the kinetic energy of the particle will then satisfy this equation. And then the time reparameterization equation will simply be this, where x of u is simply identified with j of u. And as a consequence of this equation and that equation, if you put these two equations together, there's a total conserved energy now. So this conserved energy has three parts. So this part is simply the mass of the black hole, or twice the mass of the, half the mass of the black hole. And then this is the interaction energy, including the self-consistent string tension, the confining potential, and this is the kinetic energy of the particle. And this together is the total energy is simply conserved. Okay, let me not go through all the details so you can set up initial conditions. These are a bit boring. I just simply set up initial conditions, say somehow, and I study the system. So initially the way I do it is, so what you can see is that when you completely solve it, the total energy of course is constant. That's a check of your code. If your code is wrong, you will not get it. And the black hole mass actually decreases, but it again stabilizes self-consistently. And the kinetic energy of the particle actually increases, but it also stabilizes. The interaction energy actually decays and becomes 0. So this is how it behaves in a typical way. So you see that the kinetic energy, so what happens is that the particle gains some kind of a terminal velocity, and then it simply stays like that. But this is a consequence of the full nonlinear equations of motion, and not simply that. And I think here Loga's comment will become important, because it is a bit weird, because what is happening is the source actually has a final steady state velocity, but O of u will actually decay in time, and this certainly cannot be understood by linear response. The fact that it is happening, that O of u is decaying, although x of u is growing in time, has to do with the redshift effect. So it has to, so when you convert O of tau doesn't decay, but when you take O of tau times tau prime with appropriate power, as Loga made a comment, indeed the effect is that it decays. So the redshift actually makes the interaction energy go away or become completely irrelevant. And this is something that might explain some puzzling phenomena, like for example, you take an atom and heat it up, it will definitely not remain stable. But if you do lattice gauge theory, you find that there are some kind of di-quarks, or recently also there is some evidence that some quarkonia are kind of stabilized. They simply don't melt, although you are heating it up. So they become like loosely strongly correlated system. And this might be an explanation why it happens, because what happens is that because the NAdS2 is acting like a pump rather than a dump, it actually helps to, it initially, instead of pumping energy, it pumps energy to the particle, and then it stabilizes into a terminal velocity. Something like that may happen. However, of course, so there's a coupling called lambda here, which we have introduced there. And if this lambda is if made very large, what you can show is that what is happening is that suppose if you start with, so we can simply look at what is the final value of the, what fraction of the total energy is carried by the kinetic energy of the particle at the very end, and what fraction is carried by the black hole. Because the interaction energy is 0, the total should sum to 1. So when lambda is equal to 0.14, the final energies are exactly the same. And when lambda becomes around 0.17, what happens is the black hole mass becomes negative. So it simply means that the whole setup basically becomes completely meaningless. I don't know what it actually means. Probably it means fragmentation or something else, or we have no clue. So we have to understand this better. And probably Sandeep's comment is relevant, that we have to understand exactly what is happening in the geometry, how the dialectron is actually behaving in the bulk. And that will tell us probably how we should continue, I don't know, or what we should do in that situation. Anyway, so this is the results that we have. And for the conclusions and outlook, I have nothing more to say.
That the left-hand behavior is expanded in coordinate
No, here you will not see that because the late time behavior is simply not given by linear response theory. It's a very complicated steady state solution.
Yeah, wait, eventually you settle down to a black hole, right? Or not?
Yeah, yes, we do.
So then it should be modes around that line.
Yes, but what can happen, of course, is that there are many, okay, so even though you settle down to a black hole, the SL2R charges may not settle down. They can simply, you can be in a rotating orbit on the same.
But you can rotate those back to the black hole?
No, if it has a non-trivial rotation, then it will be more like a steady state rather than a.
No, wait, sorry, I'm not understanding. Is there a unique black hole solution up to symmetric transformations of these problems?
No, because the thing is that what can happen is that, okay, so the black hole solution is of course unique, but what you can have is that you can have a situation where you just simply change the SL2R frame without changing the Casimir.
You're saying that I don't understand this very well, but you're saying there is no unique black hole solution?
No, I'm not saying that there is no unique. You won't call it a black hole solution in that case. You will essentially what I'm saying is that you can have a non-trivial SL2R frame rotation even though the Casimir is held constant. So the mass is constant, but simply, but I mean there are many things that can happen. In our case, what we find is as follows, that these kind of redshifts are actually responsible for this decay, and you have some non-trivial SL2R frame at the end of the day, which is simply not the SL2R frame you started with.
But I see. But independent of frame, if you've got a solution and you want to see something approaching that solution,
some linear response above the solution, yes. Yeah.
You can't do that?
Yeah, that should be possible. We haven't done it. But the late time solution is a very complicated solution. It's not simply this solution which we started with, or solution of this form.
I need to understand that maybe over lunch. But it's not in after doing some coordinate change or something, it's not just a standard black hole? I thought it has to be, right? Don't things settle down into black hole?
No, it does. It does apparently, but actually we are just simply beginning to understand this solution better. I can't, but I'm pretty sure that these results are correct, but we have to understand this computation and what it actually tells in a better way. So that is why we haven't actually published yet the paper, and I thought that giving a seminar here could be a good question.
But you think that it is in some frame or something like that, some coordinate choice, it is a black hole, right? Or not? That's qualitatively very important.
I can't answer, sorry. The thing is that, well, if the SL2R charges also settle down to constant values, your answer has to be yes.
And they don't?
I don't know. We haven't really. We have to say. I think they do probably also.
What can it be? It has to be ADS2.
Hmm.
Don't you think?
Yeah. So the game is always like that. There is always some ADS2. It's just simply.
ADS2 maybe with some identification.
What about the boundary value? So locally make it possible you want.
Okay, maybe the answer should be yes. What you are saying, it has to be yes.
In your talk, you told us that you classify the solutions to Schwarzschild prime was equal to 0, right?
Actually, I have the plot for the SL2R charges when without the semi-holographic case. They do settle down, but you get a non-trivial SL2R frame at the end of the day, which is actually but relative difference of SL2R frames could also be physical, because suppose if you throw in a null geodesic inside the ADS2, you get the same ADS2 on the other side, except that is SL2R shift. SL2R charges have changed. So there is something that happens similar. So it's like a gravitational memory effect. And it does happen that you get a black hole at the end of the day if you just study a normal quench. And I think the answer is also yes here. I just don't remember offhand what we get. But I think the answer should be yes also.
And then you should be able to look at the approach to equilibrium and expand it to polynomial.
Yeah. Except that what one has to recall that if you choose a non-trivial SL2R frame, then a redshift factor can be important, because if your tau of u is simply u, right, there is no redshift involved. But if there's a tau of u which is not u, because you have chosen a non-trivial frame, then the actual O of u which you measure is, as Loga was saying, is a redshifted version of it. So this is actually the catch here. The thing is that the final SL2R frame you cannot decide. The final SL2R frame is what comes out from the dynamics. You cannot decide it. And this is where the catch lies here.
Okay, maybe we should.
Okay, that's all. So, thanks.
Hello?
I see.
Oh,
Yeah, so, I have just one question.
yeah.
Can you hear me?
Yeah, we can hear you, Loga, very well.
Yeah. So just, like, do you have an idea of, this is kind of a follow-up of the previous question. What happens to tau of u? So you say tau of u at large u becomes linear in u? Is that
No. I said that if it becomes linear in U, because the initial SL2R frame was like that. Maybe I should. Our initial SL2R frame was that it was linear in U. That is, all the SL2R charges vanishes except the Q0. So that is,
so
yeah.
What happens at the u is very large?
Yeah,
It is
so,
not linear.
so when U is very large, we get a situation something like this, which is, let me show you. We get a situation like this when none three of the SL2R charges vanishes. So which means that tau of U is not simply U. It's an extremely complicated function of U. And that brings in and that is important for the redshift of O of U. So that brings an extra redshift factor.
SL2R transformation of u, right? Do you know the SL2R transformation?
Yeah. That is of course a bit complicated to describe, but it is in T of U is rather simple, but tau of U will be a bit complicated, but you can describe it. Yeah.
T and tau are
constant SL2R.
No.
It's
T.
some number, right? It's some three number, constant numbers. You
Let me-
here you go to infinity. You can find the SL2R frame.
Yeah, you can because if you know, you can of course find the SL2R frame, and we have specifically found it also. So you know that any SL2R transformation on T of U can be lifted to some transformation of tau of U. And you can compute this SL2R charges in terms of T of U also and get the SL2R frame at the end of the day. Yeah. So then of course it involves some kind of redshift factor as you're mentioning, and that probably does the trick here, this unusual trick. So I wouldn't say that I have a complete understanding of it, because apparently the solution breaks diffeomorphism invariance, and also any specific solution also breaks SL2R symmetry explicitly, because any solution of the Schwarzian will break the SL2R because it chooses a frame. And this is something we don't understand actually. How does this all reflect together in this peculiar behavior we are seeing?
But if the future time is just very dilated, then you will just see the energy go down, right? Maybe that's what is okay. My guess is that's what's happening.
Maybe what you're saying is the redshift could be important. Yeah, the fact that you have chosen a non-trivial SL2R frame could bring in this kind of extra dilatation factor. This,
Value of the Schwarzian is independent of frame, right? Or not?
the value of the Schwarzian itself is indeed independent.
Independent of frame. And that was what you were using to measure the mass.
Yeah.
So that's telling you the frame rotation can't change the mass.
But Schwarzian depends on SL2R, right? It turns out some in a very nice way, but it does depend on SL2R.
Does it? Does the value of the Schwarzian depend on
No, it doesn't actually. Each of U itself should not, but O of U and O of U does depend on the SL2R frame. O of U and X of U does.
So this I don't understand, because Schwarzian, should transform like, with there's a inhomogeneous term and then there's a homogeneous term, right?
The Schwarzian in tau of U has this two terms, which is, let me see where it is.
Isn't there inhomogeneous term? Isn't the Schwarzian like a Christopher symbol kind of a transformation? It's not like Christopher symbol, but it's an inhomogeneous term exactly to understand how the anomalous transformation of the inhomogeneous symbol.
Yeah, there is a half tau prime square, which is, and the thing is that this Schwarzian goes to this, so with an extra factor of half tau prime square, yeah. So, but what we are actually plotting is the whole term, this whole term is independent of the SL2R frame. That is what we have plotted there. So that's the black hole mass that we have defined. So indeed, that should be independent of SL2R frame. But my only thing was that the fact that the interaction energy is going down could be a fact of an explicit SL2R frame selection, but I'm not sure now. Because it could be that the Schwarzian is SL2R independent, but the other terms, of course, they break SL2R invariance. And specifically that you are choosing a J of U, that also breaks everything almost. So I think this is a reason could be that there could be some of this effect that why the linear response itself cannot capture this behavior, that O of U is decaying as a function of time. But anyway, I think I am myself probably not so convinced about the results, so I have to.
Yeah, but there's a very easy way to check. That is
Yeah.
just track the horizon and check whether the entropy on that horizon increases or not. Because there'll be some theorem, right? You've got the solution numerically. You can track it.
Yeah, entropy is given by the now the Wittgenstein Hawking entropy is what it's given by the value of the because the area is just a point area of the point.
Yes.
But the dilaton will be in which geometry now? It will be in this actual M of U in the original JT geometry. Okay.
Loga, are you through? Loga, do you have follow-up questions? Okay. Okay, excellent. Mumbai.
Okay,